Okay, so for this video we're gonna deal with series of non-negative terms, which are a series just like this one in which well, it doesn't matter if this is a 0 or a 1, right? Remember, in which the terms of the sum are all greater or equal than 0. Okay, for all natural numbers every element is positive. Okay, so if we go for the partial sums as we saw the other day, so we have S1 is A1. Okay, so let me check this. This is not from 0, from 1. Sorry. So S1 is A1, S2 is A1 plus A2, okay, and then we keep going up until S sub k, which is A sub 1 plus A sub 2 plus blah 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 plus A sub k. Okay, so this is the sequence of partial sums. Okay, partial sums. Well, this is an increasing sequence. Okay, if we take S sub k minus S sub k minus 1, what we get is A sub k, which is greater than 0. Okay, so the difference between the two consecutive terms in the sequence is greater than 0, which means that this sequence is increasing, monotonically increasing. Okay, as we saw in unit 3 about sequences. Okay, so either this, so that means that the values of if you go from, this is n 1 2 3 3 and so on, and these are the values of S sub n, the partial sums, this is increasing. Okay, so there are two possibilities. The sequence of sums is bounded above, and then the sequence is convergent, right? So that means that this series will be convergent, right? Series from n equals 1 to infinity of A sub n is smaller than infinity, or it is unbounded. Okay, and in this case, this sequence, the series will be divergent. Okay, that means that this will be equal to infinity. Okay, and also, as we saw in the unit 3 of sequences, the convergence of the series will not change if we take any subsequence. Okay, so if we do from, let's see, k equals 0 to infinity of A sub n sub k, where n sub k is a rule by which you take elements here, the convergence of these subseries, or if you want, right, if you can think of as this subsequence of this sequence of partial sums, the convergence of this series will be the same, is the same as the convergence of the original series. Okay, so this is a fact that is very useful in computations, and we will use it in some of our demonstrations as well as proofs for some theoretical results. Okay. Okay, so now oh yes, and so furthermore, if a series is convergent, a series of non-negative terms is convergent, if convergent, then this series will be, we can call it A. Okay, and if we have a different convergent series, for instance like this, we can operate with them just like real numbers. Okay, because they are real numbers. Okay, so this will be A plus B, so you can sum them, you can multiply them. Okay, so that's a very interesting properties of this series, and this is because these series are, they're absolutely or inconditionally convergent, but absolutely convergent. Okay, automatically. So if they're convergent, they're absolutely convergent. We will see what's absolutely convergent later on in the unit. But so far, just get the fact that if a series of non-negative terms is convergent, then we can operate with it as if it was a number, okay? Because it's a number, okay? So having said that, we now have, there's a lot of tools or tests to check if a series is convergent or not, okay? There are like a million of them because everyone discovers new ones every year, okay? So we will see some of them, actually 5 of them here, because I don't want you to get bored so easily with them. And with them you can actually decide the convergence of mostly every series that you will find, okay? So it's a sufficient set of tools for you guys, okay? So the first test is what we call the comparison test, okay? Okay, so suppose we have 2 sequences, okay, A sub n and B sub n, such that every element in this sequence A sub n is smaller or equal than the elements in B sub n, okay? And both sequences are positive or greater than 0, non-negative, right? Then the series that we get by summing the terms in the sequence, okay, remember the difference between a sequence and a series, which is a sum of terms of a sequence. Well, if the series of B sub n, of the terms of B sub n, which is, the term B sub n is always greater than A sub n, if this sum is convergent, smaller than infinity, then it means that the sum of the terms in A sub n, that series associated with the sequence, is also convergent. And alternatively, if the series of A sub n is divergent, I mean it goes to infinity, then it implies that the sequence, the sum of the terms of the sequence B sub n will be divergent as well, okay? So the proof for this is easy, which means it goes like this: the sum from n equals k1 to k of A sub n, well, this is smaller than the sum from n equals 1 to k of B sub n, right? Because every A sub n is smaller than B sub n, right? So if you have A sub 1 is smaller or equal than B sub 1, and A sub 2 is smaller or equal than B sub 2, and so on and so forth up until B sub n. Well, if you sum all of these parts of the inequality and you sum all of these parts, the result is still an inequality, okay? That's what we're saying here, okay? Up until A sub k and B sub k, sorry. Okay, well, now this is by definition smaller than the sum from n equals 1 to infinity of B sub n, because every term in B sub n is positive, okay? So if you sum more terms, this will be greater, okay, at least. Now, starting from the first assumption, okay, if this is, we assume this is convergent, that is, this is smaller than infinity, then this thing will be smaller than infinity, okay? So the sequence of partial sums related to A, so for instance this is, we call it A sub k, A sub k is bounded, is smaller or equal than some value B, which is the value of the series, okay? If we call B is equal to the sum from n equals 1 to infinity of B sub n, okay? This is the value of this of the series. Then every partial sum A sub k is bounded by B, okay? So this is this here A sub k is a sequence here of increasing terms, we just said, and it's bounded above by B, by capital B. So that means this thing will have a limit, okay? So that's the implication. The sum here will be smaller than infinity, okay? Now, also, if this sum, alternatively, if this sum is infinity, then that means that this, how to say this, as we keep increasing this, they take the limit, this goes to infinity. So this series and this one is greater, sorry, So we're in the second part now. Okay, if we take the limit from, you know, when k goes to infinity here, this will be smaller than this, smaller or equal than this. But if this is infinity, then this has to be infinity as well. So that's the proof, right? If this is divergent, then also this is divergent. Okay, and intuitively it makes sense, right? If all the terms in B sub n are greater than the terms in A sub n, and you sum this, all of this, and you get some real number, then it makes sense that when you're summing things that are smaller than this, you will also get a real number. And if you sum something that's very small and you get something that's infinity, when you sum something that's greater than the thing that you know is infinity, when you sum it, it makes sense that you will get infinity as well, right? Or not any, you know, you don't get any convergence. So yeah, so the theorem says that this condition has to be true for all n on all natural numbers, but this this doesn't have to be true. Okay, it's a very strict condition, but you could relax it and say, well, it could be that this thing is true, but for all n greater than some value n. Okay, some, you know, natural number, capital N. Why is this so? Because as we have seen before, you know, if we take any finite number of elements in a series and we take them out of the series, they don't really matter for the convergence of the series, right? Because it's just a finite number of terms. So if you have, you know, for instance, a sub 1 plus a sub 2 plus blah 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 plus a sub n, and then a sub n plus 1 plus a sub n plus 2, and so on and so forth, right? And then you have b sub 1 plus b sub 2 plus plus b sub n plus b sub n plus 1 plus blah blah blah. Okay, well, if we don't care about these terms, okay, these terms will be equal to something, let's call it a sub 1, and these terms will be equal to something, let's call it b sub 1. Okay, well, starting from here up until the infinity, then we have that a sub n is smaller than b sub n, right? This is a rule that we got. Then we can apply, starting with this series, starting with sequence starting here, we can apply this theorem. Okay, and then so if this sequence is if this sequence is convergent, then the whole sequence will be convergent, because, you know, for instance, if this starting in b sub n plus 1 is equal to b2, then the whole series will be b1 plus b2, right? And then we know that this sequence will be also convergent. Okay, do you see? Okay, so I'll leave you with two exercises to apply this test. The first one is to show that the sum of 1 over n factorial from n equals 0 to infinity is a convergent series by comparing it with the geometric series. Okay, and well, if you're wondering about n equals 0, the definition of 0 factorial is 1. Okay, this is just a convention. Okay, don't worry too much about it. And the hint is to note that n factorial is greater than 2 to the n for n greater than 3. Okay? And the second exercise is to show that the sum from n equals 2 to infinity of 1 over the logarithm of n is infinity, comparing it with the harmonic series. Okay? Okay, so next test. This is slightly more complicated test. It's called Cauchy's condensation test. So Cauchy was a French mathematician in the 19th century. Okay, very important and influential guy in the development of calculus at the end of the 19th century and beginning of the 20th century. Okay, most of the results that we have today in calculus are due to him. Okay, so Cauchy's condensation test, so it says if a sub n is a sequence, is a monotonically decreasing sequence of non-negative terms, then the series, okay, the series, so the sum of all the terms of this sequence a sub n being convergent implies that this subsequence, so this another series, the sum from k equals 0 to infinity of 2 to the k of times a sub 2 to the k is also convergent, and the other implication applies. Okay, so this means two implications that we need to prove. So the first one is that the sum of n equals 1 to infinity of a sub n smaller than infinity implies the sum from k equals 0 to infinity 2 to the k a 2 to the k is convergent, and the other way around, right? 2 to the k times a 2 to the k smaller than infinity is, or it's convergent, implies that the series from n equals 1 to infinity of a sub n is also convergent. Okay, so I'm gonna try and explain the proof for this theorem. Okay, so the idea here is that we can try to bound these terms in this sequence by a sum of these terms by a sum of terms here. Okay, so let me explain. So we have a sub 1 is equal to 2 to the 0 a 2 to the 0, right? So this a2 to the k means that 2 to the k is the index of these elements. Okay, so when k equals 0, then 2 to the k is 1. When k equals 1, 2 to the k is 2. When k equals 2, 2 to the k is 4. Okay, so we're just taking the terms in the sequence that are whose index is the power of 2. Okay, so we have a sub 1, a sub 2, a sub 4, a sub 8, a sub 16, a sub 32, and so on and so forth. Okay? Okay, so then a sub 1 is equal to, so 2 to the 0, a sub 2 to the 0, right? Now, a sub 2 plus a sub 3 is smaller than 2 times a sub 2. Why? Because the sequence is monotonically decreasing, right? So a sub 3 is going to be smaller or equal than a sub 2. Okay, so if you sum a sub 2 to both sides, you have this inequality. Okay, and we can rewrite it like this: 2 to the 1, a 2 to the 1, right? Now let me erase this. Now a sub 4 plus a sub 5 plus a sub 6 plus a sub 7 is smaller than 4 times a sub 4, right? Because a sub 5 is smaller than a sub 4, a sub 6 smaller than a sub 5, and so on, right? And we can write it 2 to the 2, a 2 to the 2, okay? And as you can see, we can think of generalizing this and saying a sub 2 to the k plus a sub 2 to the k plus 1, so this is the index, then a sub 2 to the k plus 2 plus, and all of them up until a sub 2 to the k plus 1 minus 1. Okay, so this would be a to the 2 to the cube minus 1. Okay, so a sub 8 is 2 to the cube minus 1. This is smaller than 2 to the k a 2 to the k. Okay, so, and again, we could prove this using induction, okay, but we are not going to do it. Now if we sum every let's see, how can I do it? If we sum all of these inequalities right here, okay, we sum them, then we'll get here. Okay, the left hand side is just the sum from n equals 1 to 2 to the k plus 1 minus 1 of a sub n, right? This is the sum. and this is smaller or equal than the sum from k equals 0 to 2 to the k, sorry, or no, to, sorry, yes, I have to change this. So for some value p, right, p plus 1, okay, and so this is from k equals 0 to p, right, of 2 to the k, a 2 to the k, okay. So I've just changed here the last term here, instead of being k, I've just changed it to be p, okay. Or I could rewrite it, maybe it's easier for you guys if I write it like this. 2 to the k plus 1, k, p equals 0, and then this is 2 to the p, a 2 to the p, okay. So the sum from n equals 1 to 2 to the k plus 1 minus 1, okay, of a sub n, so a sub 1 plus a sub 2 plus a sub 3 plus a sub 4 plus all of these terms and up until this one is smaller or equal, okay, we're just summing inequalities of this sum from p equals 0, okay, up until k of 2 to the p, a 2 to the p, right? Do you see? So if this if we take the limit when k goes to infinity in both sides, okay, the limit when k goes to infinity, and here what we have is this goes to infinity and this goes to infinity, okay, so we have infinity and infinity. So starting in the second implication, if this thing is smaller than infinity, this is convergent, then this thing will be convergent as well, because it's smaller than this, right? And this is kind of, this is using the comparison test that we have just seen, okay? So if the this subsequence multiplied by 2 to the k is convergent, then we know that this original series is convergent, okay? And now let's see the other way around. We have that a sub 1 is greater than a sub 2, right? Because it's a decreasing sequence. And a sub 2 is 2 to the 0, 8, 2 to the 1. Or you could say 1/2, 2 to the 1, a 2 to the 1. Okay? Now, a sub 2 plus a sub 3 is greater than 2 times a sub 4, right? Because both a sub 2 and a sub 3 are greater than a sub 4. And this is just 1/2 of 2 squared of a2 squared, right? And we can keep doing this. a4 plus a5 plus a6 plus a7 is greater than 4 times a8, right? Which is 1/2 of 2 cubed a2 cubed. And we can keep doing this, and so we have a 2 to the k, sorry, and in the sub-index, a 2 to the k plus a 2 to the k plus 1 plus blah 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 plus a 2 to the k plus 1 minus 1, okay, just like before. This is greater, sorry, this is greater or equal than 2 to the k a 2 to the k plus 1. And we can rewrite it like this, like 1/2 of 2 to the k plus 1 a 2 to the k plus 1. Okay, now just like before, we can sum all of these terms in the left hand side, all of these terms in the right hand side, and we get that the sum of n equals 1 up until some value 2 to the k plus 1 minus 1 of a sub n is greater than 1/2 of the sum from p equals 0 to k of 2 to the k a2 to the k. Okay, so if this is smaller than infinity, well, again, we can take limits in both expressions, so then you get this is infinity, this is infinity. So if this is convergent, okay, so we're trying to prove the first implication now. If this is convergent, okay, smaller than infinity, this is going to be greater than this, okay? And so because multiplying a series by 1/2 doesn't change its convergence, then we know that this series here is also convergent using the comparison test. Okay? Okay, so that's the proof. Okay, you can review it if you're not convinced, or if you don't understand something. You can also ask me whenever. But the important thing now is that we have a strategy to test if some series are convergent or not, and we're going to do a couple of examples. Okay, so the first one is this series. Okay, so this is what we call the Riemann series. It's also called the generalized harmonic. Okay, it's easy to see that if alpha is 1, then this is the harmonic series that we have seen. Okay, 1 over n, and we know that this is divergent. Okay, but what happens for other values of alpha? Is this convergent or divergent? Well, let's see. Okay, we're going to apply Cauchy's condensation formula. Okay, so we have a sub n, so a sub n is 1 over n to the alpha. Okay, and we need to compare it with 2 to the k a 2 to the k, so this is 2 to the k 1 over 2 to the k to the alpha, right? Okay, so this is the series from k equals 0 to infinity 2 to the k divided by 2 to the alpha k. Okay, right? Can we see if this is convergent or not? Well, we can operate here. This is k equals 0 to infinity, and then this is 1 over 2 to the k alpha minus 1, right? But then we can apply the properties of the exponential and say this is 2 to the alpha minus 1, everything to the k, right? Okay, so now if you think about it, this is the same as saying this is k equals 0 to infinity of x to the k, where x is 1 over 2 to the alpha minus 1, right? But this is the geometric series, right? And we know that the geometric series converges where the absolute value of this x is smaller than 1. Okay. Now this is positive, so that we can operate with this. This is equal to 1 is smaller than 2 to the alpha minus 1. Okay. And if we take logarithms, we have 0 is smaller than alpha minus 1 logarithm of 2. Okay, so again, alpha minus 1 times the logarithm of 2. The logarithm of 2 is a positive number, so the only way that this thing cannot be 0 is if alpha is negative. Okay, so this implies that alpha has to be greater than 1 for this series to be convergent. Okay, so let me recapitulate here. What we have proven is that if alpha is greater than 1, then this series is convergent, the Riemann series. If alpha is smaller or equal than 1, it will be divergent, okay, just like the harmonic series, sorry, the geometric series. Okay, so that's very interesting. So you have the sum of 1 over, for instance, n squared or n cubed or something like that. Everything like that will be convergent. But if you have, for instance, the sum from n equals 1 to infinity of 1 over the square root of n, this is not convergent. This is divergent. Okay, so remember that. If alpha, this is a very important result. Okay, so you need to remember that the convergence of this series as a function of this parameter alpha. Okay, and so if because we will use them for the comparison test and for other tests that we will see later. Okay, so remember that. And okay, another example is, it's useful to, the Cauchy's condensation test is useful when you have logarithms. So for instance, this from n equals 2 to infinity of 1 over n times the logarithm of n to the alpha. Okay, so this is a sub n is 1 over n times the logarithm of n to the alpha. Okay, so again, in order to study the convergence of this, we will say from k equals 0 to infinity of 2 to the k and a, but instead of writing n here, we have 2 to the k, so we have 2 to the k, and then we have the logarithm of 2 to the k to the alpha. Okay, so then we have let's see, 2 to the k and 2 to the k cancel each other out, so then we have the sum from k equals well, in this case it has to be 1, right? Because if k equals 0, then the logarithm of 2 to the k is, so 2 to the k is 1, the logarithm of 1 doesn't exist, so this is from 1. Okay, k equals 1 of 1 over, and this is exactly the same as k logarithm of 2, right? So this is k to the alpha logarithm of 2 to the alpha, but we can take the logarithm of 2 to the alpha outside the sum, right? And then we have the sum from k equals 1 to infinity of 1 over k to the alpha. But this is just the generalized harmonic series, or the Riemann series that we have just seen. Okay, so this original series will be convergent, okay, if alpha is greater than 1, and divergent, sorry, not greater than infinity, equal to infinity, if alpha is smaller than or equal than 1. Okay, just like before. Okay, so you can see the usefulness of this test. Okay, now the next test is what we call the limit comparison test. Okay, so the idea is that just like when we saw sequences that are asymptotically equivalent, this means that when they are close to infinity, or when the index is very large, both sequences have very similar terms. So that means that if you sum them, you will get similar values. So the idea is that if you have two sequences that are asymptotically equivalent, then if one is convergent, then the other will be convergent, and the other way around. Okay, so sorry, if one is convergent, then the other is convergent, and if one is divergent, then the other is divergent. Okay, so the convergence, if two sequences are asymptotically equivalent, then the series associated with them, okay, remember it's not the same, the series and the sequence, the series associated with these sequences will have the same convergence. Okay, now if a sub n is negligible in comparison with b sub n, the series associated with b sub n being convergent implies that the series associated with a sub n is also convergent. And you can see this is kind of similar to the to the comparison test, which this means that the terms of a sub n go to 0 much faster than the terms of b sub n do, right? And the other way around. So if the series associated with a sub n is divergent, then this means that the series associated with b sub n is also divergent, especially because if the terms that go, if a sub n go to 0 very, very fast, much faster than b sub n, which means that at some point the terms of b sub n are much larger than the terms of a sub n. Well, if this sum goes to infinity, then it's reasonable to think that this also goes to infinity. Okay, so this is what this is saying. This is similar to the to the comparison test. It's just that you don't need to make sure that every term is greater than the other one. Okay, So some example of this, we have this series, okay, sum from n equals 1 to infinity of 1 over the square root of 3n squared plus 2n plus 7, right? Well, you could say, well, the square root of 3n squared plus 2n plus 7 is, we know it's asymptotically equivalent to 3n squared, because these terms are negligible in comparison with this, right? And this is exactly the same as square root of 3 times n, okay? So then the series from n equals 1 to infinity of 1 over the square root of 3 times n, which is none other than this, 1 over the square root of 3 times the series from n equals 1 to 1 over n. This is just the harmonic series, okay? And we know this is divergent, okay? This is non-convergent. But because these two sequences are asymptotically equivalent, what you could say, and then this sequence is also going to be divergent, okay? So that's the idea behind this test, okay? So as an exercise, prove using appropriately the limit comparison test that we have just seen, that if a sub n is greater than 0 for all n, then, and we know that this is true, that the limit when n goes to infinity of n to the alpha times a sub n is L, so it's a real number that's greater than 0. So this sequence, okay, this sequence is convergent, then the series of a sub n is convergent if alpha is greater than 1, and it's divergent if alpha is smaller or equal than 1, okay? So just, it won't take you long, just using the limit comparison test, you think a bit about this and about the examples that we have seen about the Riemann series, and then you will have a result, okay? And finally, the last two tests that we will see. The first one is what they call the root test, okay? So then again, a sub n is greater than 0, so this is a sequence of non-negative terms, and the limit of the nth root of this sequence is L, okay? So this is, we haven't gotten to the series yet, okay? We have a sequence of terms. The nth root, the limit of the nth root of a sub n is L, is a positive number, right? Then this means that the series of a sub n is convergent if L is smaller than 1, and it will be divergent if L is greater than 1. And the case L equals 1 remains undecided, okay? And so what's the idea behind this? This is using the limit comparison test. If this is true, okay, the limit of this is true, then we can say the limit when n goes to infinity of a sub n, the nth root of a sub n divided by L, okay, is 1, right? Because we are dividing both expressions by L, sorry. So we could say that the nth root of a sub n is asymptotically equivalent to L, right? But this can also be written like a sub n is asymptotically equivalent to L to the n, right? So that means that this series, the convergence of this series, a sub n, is the same of this series n equals 1 to infinity of L to the n, right? And this is the geometric series. We know that this is convergent if L is smaller than 1, okay? And if L is greater than 1, then this will be divergent, okay? Let me write it here. N equals 1 to infinity. This will be divergent if L is greater than 1. And if L is equal to 1, then we need to study each case separately, okay? And use the definition, but we will do exercises and you will see what I mean by this, okay? And finally, the quotient test, okay? So from the root test, we can apply one of the corollaries of Stolz theorem that we saw in last unit and see that the condition that the limit when n goes to infinity of the nth root of a sub n equals L implies that the limit, sorry, not that implies that, but this, if this limit a sub n over a sub n minus 1 equals L, then this implies this, and then we have the proof for the root test. Okay, so if this is true, then we know this is true as well from the corollary from Stolz theorem. Okay, and so just like before, the convergence of the series will depend on the value of L. If L is smaller than 1, then the series will be convergent. If L is greater than 1, the series will be divergent. Okay, so keep in mind these two tests. We will use them a lot during the exercises. Okay, so that's it for this video.